Hello everyone, my name is Bangbang. Today I'm going to present our work on behalf of all the authors. The title is SRUF, Low Latency Path Routing with SRv6, Underlay Federation in Wide Area Network. I will start from introducing the motivation. Assume that you have CSAs in different areas and you want to make them communicate with each other. What will you do? First, you need to connect them to the internet, which is composed of many automation systems. Next, you need to decide how to transmit the message. You can use IPv4 or IPv6 protocol. Both of them have the source address and the destination address in their packet headers. The routing paths are decided by the wide area network infrastructure, which includes the physical devices and the protocols in control plane. Finally, with the help of a wide area network infrastructure, you can send the packets as long as you organize them as designed protocols. The most important point here is the packet is routed in the network according to the destination address only. However, sometimes the selected routing paths might go through congested links, or even the selected routing paths never consider the end-to-end latency. The neglect of latency in wide area network leads to a phenomenon which is called triangle inequality violation. It means that the latency of a direct path is larger than the latency of indirect passes. As shown in this example, TRV means the latency between A and B is larger than the sum of TLC and TCB. We have analyzed a network latency trace. We find that about 70% pair of nodes have low latency routing through one hop or two hops in direct passes. So in here, can we steer the packet through the indirect path by carrying the address of node C in the packet header? Or in more general case, can we leverage the TRV to get low latency path routing? To implement this, we need to know the latencies among routers, which can be solved by PIM program. We also need to have the ability to change routing, which can be solved by SRv6. SRv6 is a source routing that has the addresses of intermediate nodes in packet header. As shown in this example, the default shortest path between route 1 and route 3 is the direct link. With SRv6, we can add the addresses of route 2 and R3 in the packet header. Then the packet can be first routed to route 2. After reaching route 2, R3's address will be activated, and then the packet will be routed to route 3. So we can conclude that SRv6 can be used to change the routing path. After introducing the motivation, we can now introduce our solution, SRUF. How does SRUF work to provide low latency indirect routing paths? As shown in this figure, there are 4 axes in SRUF, and we assume that they have found the low latency indirect paths among them and recorded them in a table, which we call the SRUF table. In this example, there is a packet needed to be transmitted from S0 to S9. When the packet reaches S1, the member of SRUF, SRv6 daemon will intercept the packet and activate the corresponding segment and then pass it to SRUF proxy. Then the proxy will find that the S path is SC to S8 to S7 to S7 to S9 from BGP RIB. The proxy will know that this path has a low latency from SRUF table, so it will insert AS5 into the packet segment routing header. Finally, the new encapsulated packet will be forwarded to S5 according to FIB. The key challenge is how to find the low latency routing paths efficiently, which equals to how to construct SRUF table in each member efficiently. In our solution, we build a virtual network coordinate that places all SRUF members. We have designed a strategy of probing and disseminating to find a series of candidate indirect passes. Due to the time limit, you can see more details in our paper. Finally, for the nodes in different rows or columns, there are 2 square root n minus 2 candidate passes. For the nodes in the same rows or columns, there are 2 square root n minus 3 candidate passes. In this example, node 1 and node 16 are in different rows. There are 6 candidate passes. For node 1 and node 4, there are 5 candidate passes. Finally, we select the best path from the candidate set and record it in SRUF table. Next, we introduce the experiment results briefly. In the numerical experiment, we verify the efficiency of finding low latency indirect passes. We use a network with 6,000 nodes. We can find that the larger size of SRUF can perform better. The group with 60 times 6 SRUF members can reduce the average latency by 30% compared to the group with 30 times 30 size. From the CDF, we can easily find that the latencies in SRUF are smaller than them in default routing. We also emulate SRUF in RP mainnet with 42 nodes. It also shows that the larger SRUF can perform better than the smaller one. In 6 times 6 SRUF, the average latency is 25% lower than it in the default routing. Okay, it comes to the summary. In this work, we leverage TRV to provide low latency indirect passes. We provide efficient methods to find low latency indirect passes, which has a good scalability and efficiency. We leverage SRv6 to build SRUF in Underlay network core, which has good compatibility and feasibility. In the future work, we will evaluate the impacts of latency distribution in Underlay network and evaluate its performance in larger scale emulation experiments and testbed experiments. So that's all. We welcome all the questions. Thank you.